Example 1. Are people getting taller? Listed below are heights in millimeters of randomly selected U.S. Army male personnel measured in 1988 from dataset Answer 1 1988, and different heights in millimeters of randomly selected U.S. Army male personnel measured in 2012 from dataset 3 Answer 2 2012. We want to use a 0.05 significance level to test the claim that the mean height of the 1988 population is less than the mean height of the 2012 population. Now there is a correction in here that I need to make here. This number right here, this third one here, should be 1734. Okay, so the first thing we want to do is we're going to do the following. We want to identify and let answer 1, 1988, be population mean 1, and let answer 2, 2012, be population mean 2. So, first thing we want to do is use StatCrunch to find the sample mean of the sample for the first one, and find the standard deviation and the sample size. So what you want to do is you're going to open up StatCrunch, and then you're going to enter the data. So you can see here I put in the title for each column. So the first column represents sample 1, and then the second one is sample 2. So we're going to go ahead and select Stat. We're going to go to Summary Stat and select Columns. And so we're going to select both columns. And then again, we want to find the mean. We want to find the standard deviation, and then we also want to find the sample size for all of them. And then we're going to go ahead and then select Compute. Okay, so therefore it gives us that information. I'm going to go ahead and copy this. So now we have this data. Now we can go ahead and then write our information. So you can see here that the mean for sample 1 is 1739.417, rounded 3 decimal places. We can see that the mean for sample 2 is 1777.8. Sample standard deviation of 1, rounded to 6 decimal places, is 66.601199. And the sample standard deviation for sample 2 is 47.866183. The sample size for sample 1 is 12, and the sample size for 2 is 15. Now we need to take a look at the requirements. So for 1, the values of the 2 population standard deviations are not known, and we are not making an assumption that they are equal. Number 2, the 2 samples are independent because the measurements are from different people, and they are not matched or paired in any way. And number 3, the samples are simple random samples. And number 4, both samples are small, 30 or fewer. So we need to determine whether both samples come from populations having normal distributions. So the normal quantile plots and the 2 samples suggest that the samples are from populations having distributions that are not far from being normal. In order to do that, we want to make sure that we can find the QQ plots. So let's go ahead and do that. So we're going to go to Graph, select QQ plot, and then we're just going to select both of them. Okay, and then what we're going to do is just add the horizontal lines and the vertical lines, and then select Compute. So if you take a look at the first graph represents the first sample, and you can see that it looks like a normal distribution. If we go to the next one, again, you can see the sample 2. Again, this represents a normal distribution. So therefore, all the requirements are satisfied. Okay, now we want to be able to state the claim and the opposite of the claim. Okay, now the claim is that the mean height of the 1988 population is less than the mean height of the 2012 population. So if we come back up here, it says less than. So therefore, we're going to take a look at the claim. So the claim is that population mean 1 is less than population mean 2. And therefore, the opposite of that claim would then be that the mean population 1 is going to be greater than or equal to population mean 2. Now recall that the null is always going to contain the equality. So therefore, the null is going to be population mean 1 is equal to population mean 2. And therefore, the alternative is going to have the claim where population mean 1 is less than population mean 2. Therefore, we can then state and identify the null and the alternative hypothesis in step 4. So the null, we have population mean 1 is equal to population mean 2. And the alternative, population mean 1 is less than population mean 2. Okay, now in step 5, we want to use the alternative hypothesis to determine whether it is a left, right, or two-tailed distribution. Now this is a left-tailed distribution since the alternative hypothesis contains the inequality that is less than. Okay, now we're going to select the significance level alpha. Well, in the problem it states that alpha, or the significance level, is equal to 0.05. And now we want to state the degrees of freedom, and we're going to use the simple and conservative estimate. Well, sample size n1 is equal to 12, and sample size 2 is equal to 15. So we can see that sample size for 1 is less than sample size 2. Now recall that the degrees of freedom is going to be smaller of those two. Therefore, the degrees of freedom is going to be 12 minus 1, because that's the smaller of the two, and 12 minus 1 is going to equal 11. Okay, so now we're ready to then find the test statistic. So for step 8, the test statistic for two means with independent samples, okay, with the null being population mean 1 minus is equal to population 2 with the following. So we know what the sample mean is, which is 1739.417. Sample mean 2 is 1777.8. We have the sample standard deviation of 1, sample standard deviation of 2, n1, n2, and we know that population mean 1 minus population mean 2 is equal to 0. So now we're going to plug this information into our formula. So let's go ahead and do that. So we have sample size mean 1 is 1739.417. And then we have sample size mean 2, which is minus 1777.8. Okay, and then we're subtracting the following. We're going to subtract the following, which is the population mean 1 minus population mean 2, which is equal to 0. Okay, and then we're going to take the sample standard deviation of 1, and then we're going to square it. So we're going to take that value and square it. Okay, and then we have sample standard deviation 2, and then we're going to square that in the other numerator of that fraction. And then what we're going to do is now we're going to divide it by the sample size for n1 there, and then we're going to divide the other one by the sample size there, which is 15. So let's go ahead and plug this in a calculator so that we see how this is solved. Okay, so I'm going to go ahead and do the following. So in the numerator, we're going to take parentheses 1739.417, and then we're going to subtract 1777.8. Right? And then we're subtracting 0. If we subtract 0, we're still going to get the same number. So therefore, this is what we're going to get in the numerator. Now we're going to select divide by. And then what we're going to do is we're going to divide that by second square root. Now I want to point out here that we need to add parentheses where needed. So that means that we need to put an extra parentheses around here, an extra parentheses around here when we're putting this in our calculator. So let's go ahead and do that. So we have one parenthesis for the outside and then another one for the numerator, which is going to be 66.601199, and then we're going to square that, and then we're going to divide that by 12, and then we're going to close the parenthesis. And now we can go ahead and then put plus, and then we're going to add a parenthesis and then another parenthesis, and then we're going to put that inside that parenthesis, which is 47.866183. And then we're going to close the parenthesis and square that, and then we're going to divide that by 15, and then we're going to close that parenthesis and then just shift it over and then press enter. When we press enter, we're going to get the following: negative 1.679354, and we're going to round that to 3 decimal places, so we get negative 1.679 as our test statistic. Okay, now that we have our test statistic, now we can go ahead to step 9. So we're going to draw the curve and then label. So we're going to do the p-value method first and then the critical value method the second. So recall that we have our degrees of freedom, which is 12 minus 1, which is equal to 11. And we know that the test statistic is negative 1.679. So let's go ahead and then draw our bell curve. Okay, and then label. So we draw our bell curve. Go ahead and do that again here. So we draw our bell curve. We know that our mean is 0. Okay, we know that our degrees of freedom is 11. Now let's go ahead and put in our test statistic. Now it's a left tail, so we know it's going to be on the left side. And our test statistic is negative 1.679. And so what we want to be able to do is we want to be able to find that p-value. And the p-value is going to be located in this area here. So to find that p-value is going to be the following. It's going to be the probability of when that test statistic is going to be less than negative 1.679. So let's go ahead and use our StatCrunch. So we're opening up StatCrunch. Okay, now recall here that this is a t-test statistic, so we're going to go to Stat, go to Calculators, and then scroll all the way down to t. Okay, we want to make sure that we put in our degrees of freedom, which is 11. And then we have less than, so it's less than, and then we're going to put in our test statistic, which is negative 1.679. And therefore, there is our p-value rounded to 4 decimal places, which is 0.0606. So we get 0.0606. So therefore, here we can see that our p-value is equal to 0.0606. Okay, so now we want to make a decision. So for step 10, reject the null if the p-value is less than or equal to the significance level. And we fail to reject the null if the p-value is greater than the significance level. When comparing the p-value versus the significance level, we see that the p-value of 0.0606 is greater than 0.05. Therefore, we fail to reject the null hypothesis. Now, let's go ahead and use the critical value method here. So, what do we need to know? Well, we know that the test statistic that we found is negative 1.679. We also know that the degrees of freedom is 12 minus 1, which is equal to 11. Now we need to find the critical values. Now, recall that the critical values are dependent upon what alpha is. Well, alpha is equal to 0.05, and we're dealing with a one-tailed distribution. So let's go ahead and do that. So if we come over here, and we know it's a left-tailed distribution, let's go ahead and select refresh. Okay, we know our degrees of freedom is 11, and we know it's going to be less than or equal to. Now we're going to put in the area of 0.05. When we put in the area of 0.05, we're going to get a critical value rounded to 4 decimal places to be negative 1.796. So therefore, there is our critical left tail value. So now we can go ahead and draw our picture. So we're going to draw our bell curve. Noting that we have 0 as our mean. Okay, and then we're going to put in our left critical value to be negative 1.795. And now we're going to shade the critical region. So this represents the critical region. Now we need to look at the test statistic. Well, the test statistic is negative 1.679. Okay, so it's not in the critical region. It's over here on the right side. So the test statistic is located on the right of that number. So therefore, we would say the following. Reject the null if the test statistic is in the critical region. Fail to reject the null if the test statistic is not in the critical region. And we can see here that the test statistic of negative 1.679 is not in the critical region. Therefore, we fail to reject the null just as we did when using the p-value method. Okay, so now that we failed to reject the null, we need to come back and take a look at the claim. Well, the claim is that it's less than. So it doesn't have the equality. So we know it doesn't have the equality, and we failed to reject the null hypothesis. So when we're looking at our conclusions, then we're going to select the second one here. And the second one is the following. The second one states that the original claim does not include equality, and we failed to reject the null hypothesis. So we would say that there is not sufficient evidence to support the claim that, followed by the original claim. So the conclusion is the following. There is not sufficient evidence to support the claim that the mean height of the 1988 male population is less than the mean height of the 2012 male population. Now, are people getting taller? Maybe, maybe not, but the given data do not provide enough evidence to support that claim. The sample mean from 1988 is 1739.4 millimeters, and the sample mean from 2012 is 1777.8 millimeters. So the 2012 sample mean is larger. Perhaps a larger sample might provide sufficient evidence to support the claim. Also, the sample data are from U.S. male Army personnel, and this sample might be from a population that is different from the general population.